Awesome. Thank you very much, Barack. So I'm here to tell you about Spark SQL and Spark SQL DataFrames. I'm going to get started with just a little bit of background on the Spark SQL project. So Spark SQL is the newest component of the Spark stack. It's just over a year old, I think, when we made the first commit. But in spite of being so young, it's actually one of the most active components in the Spark ecosystem today. So here's a couple of graphs, which I made using Spark SQL, obviously, that show the number of commits per month has been steadily increasing. And actually, last month, we hit a new record of almost 200 commits. And what gets me really excited is the number of contributors to the project as well as continuing to increase. So just the Spark SQL component alone had over 150 contributors total as of last month. So why are people excited about Spark SQL? What is this project all about? So a big part of it is running SQL queries, in particular using the HiveQL dialect. And it's often used either alongside or replacing existing Hive deployments. So we interoperate very nicely with Hive. We use their exact query parser, so you can bring your queries right over. We use their SERDs. We use their UDFs. We use their UDAFs. We connect to their metastore. So basically, you just drop your Hive site XML file into Spark's comp directory, and all of your Hive tables are accessible. And actually, in this most recent release, Spark 1.4, we revamped the way that we're doing multiple Hive version support. So we're very excited about being one of the few projects in the Hadoop ecosystem that can actually interoperate with multiple versions of Hive at the same time. So that's kind of the basics of it. That's what people like about SQL. And SQL is the lingua franca for doing analytics and analysis. So what this means is that now that we've got SQL on top of Spark, you can use Spark to connect to all of these existing very cool tools. So Tableau, Zoom Data, Click. You can use our JDBC server and access data that was previously inaccessible. So if you've got JSON data stored in S3 or Parquet data stored on HDFS, all of these are now available to these systems. The JDBC server is very popular because it's also a really great way to multiplex a Spark context. A question I see a lot on the mailing list is, I've got a bunch of users. I want to cache an RDD and allow a bunch of different people to share that in-memory cache. And the JDBC server makes this very easy. You can have multiple clients sharing the same cached RDDs, running interactive queries over them using SQL. But of course, it's Spark. So it's not just about typing in plain SQL queries. We actually have very rich language bindings in all of the languages that Spark supports. So Python, Scala, Java, and R. And using these languages, you can run SQL queries alongside your traditional RDD operations. So I can take the results of a SQL query and immediately drop back down into MapReduce. And going seamlessly in between these two worlds, I can take the results of one of my Spark computations. I can take an RDD, and I can turn it into a table, which I can run SQL queries over. So these rich language bindings are a reason why we think that this is quite a bit more than just SQL. And so just a little bit about myself. As Barack said, I'm the lead developer of Spark SQL at Databricks. I'm putting my Twitter handle up here because I'll be posting these slides and all of the code examples that I'm doing on there later. So if you want to follow along after the talk, check out there. But I've been talking a lot about SQL, and a lot of you are thinking, I'm a data scientist. I'm not some old guy in a suit. And so I'm here to give you the not-so-secret truth that Spark SQL has almost nothing to do with SQL. So we do really good at running it, but that was not the point. That's not why we built this project. The reason we created Spark SQL and the Catalyst optimizer underneath that powers it is to make it possible for developers to create and run their Spark programs faster. So this is both faster for you in terms of development and faster in terms of execution time. So using kind of the Spark SQL logical representation, either through SQL or through the DataFrame API, allows you to write less code, automatically read less data, so kind of use things like partition pruning, pushing down predicates into data sources to make your system go faster. And really what this all comes down to is letting the optimizer do the hard work of writing Spark jobs. These are things that SQL databases have been doing for years, and now kind of this power is available to you as a Spark programmer. At the core of this idea is this new concept that we've been talking a lot about today called a data frame. So you could think of a data frame a lot like the RDDs that you know and love, but it's a little bit different. An RDD is this opaque collection of objects. We have no idea what those objects are holding or what information in there is valuable to you. In contrast, with a data frame, we have the schema. So it's still a distributed collection, but it's broken into named columns where we know the types of those columns. And this extra semantic information makes it possible for us to run queries significantly faster, do optimizations that would not otherwise be possible. Now, of course, we didn't invent the concept of a data frame. This has been something that statisticians have loved for many years. And what we did when we were designing the APIs here was we actually looked at these other systems, R and Pandas, and what we took from them was this clean API for doing a lot of the common tasks of data science. So selecting columns that you need, performing expression evaluation on them, filtering, aggregating, removing nulls, cleaning out messy data, and then actually plotting as well. So I think this is one of the coolest features of DataFrames. I can do large aggregation over huge amounts of data, shrink it into the working set that I want, and immediately go into a Pandas data frame and use Matplotlib and all of the R visualization tools that you know and love and are familiar with. So you might be thinking, wait a second, if you've been following the project for a while, isn't that a schema RDD? And yes, it actually is. But it turns out most people don't get as excited about schema as I do. And so we decided to rename it to something everybody was a little more familiar with. But really, DataFrames are schema RDDs. It's just a more user-friendly name for them. So let's actually get into how you use these data frames. And every Spark program starts and ends with reading and writing data. And one of the nicest parts of DataFrames is this new unified API for reading and writing data in a variety of formats. I say unified because I can use this for a variety of formats in a variety of languages. So the code example that you're seeing up on the screen here is in Python, but pretty much this exact same code example will work in Scala, Java, or R as well. So kind of once you know how to read and write data with DataFrames, you can move between languages, you can move between formats without having to change anything. Let's dive in and unpack what is exactly going on here in this example. So we've added this new builder pattern to concisely specify a wide variety of options to whatever data format you're plugging into. So you always start by calling either SQL context.read when I want to load data in, or dataframe.write when I want to write data out. So this gives me a builder that I then call methods on to do configuration. So when I want to do configuration, I call these various methods. So for example, I would say format to specify the type of file that I'm reading in. And as I'll show, it's not really even just about types of files. It can also be connecting to other systems here as well. You then use options to specify any format-specific configuration parameters that I might want to set up. So in this example, I'm reading in a JSON data set. And one of the cool parts about our JSON support is we actually sample the data set to figure out what the schema is so you don't have to tell us what the columns are. So in this case, I'm saying I only want to sample 10% of the rows. And then I actually say load the data from this file on disk. And then to write out, very similarly, if I want to convert this data from JSON to Parquet to get, by the way, this will give you huge speed ups if you're reading your data multiple times. If you've got JSON data, absolutely run these lines of code. But basically, this will then write this data out as a table stored in Parquet, partitioned by year. So if I write queries over the year, Spark SQL will now automatically read only the directories for the years that I care about. And then to actually cause the operation to happen, I say load, save, or save as table, which actually interoperates with the Hive metastore, both writing the data out and registering the table with the metastore. And so what this means is, I showed JSON in Parquet, but actually there's a pretty large ecosystem, a variety of sources that you can use to read and write. So built into the distribution, we have Hive, we have Parquet, we have JDBC. And then externally, we've got libraries for reading Avro, CSV, DBase, and there are a lot of exciting new libraries that are coming out now. So both Cassandra and MemSQL have actually written custom RDDs that understand those systems and know how to use locality information to extract data into Spark SQL in parallel automatically. So you can use this then to write pretty much entire ETL pipelines in a relatively small amount of code. So in this example, I'm showing a custom data source. So I don't know how many people are familiar with Jira, but it's a bug tracking system on the internet, something that I spend a lot of my day playing around with. And so I wrote a data source for Jira, where all I do is give it my username, my password, the API to the Jira that I want to connect to, and a query, and it then returns a data frame extracting all of that data from Jira's REST API. So in this example, I'm extracting the data, and then I'm calling normal Spark operations. So I can say repartition, I can say map, I can do any kind of Spark stuff I want there. And then I can immediately write it out as a Parquet table. So this is a great way to do ETL in a very declarative, easily understandable, concise way. So once you've got the data loaded in, the next thing you need to do is you need to actually do some operations on it. And so this is where the high-level, powerful operations that DataFrames provide make writing your Spark programs easier. So like I said, you can select columns, you can do filtering, you can join with other data sources, you can do common aggregations, counting, summing, averaging. We even have window functions now as well. And then finally, once you get the results down to a small size, you can plot with pandas or R or any of these other plotting libraries. So what this means for you as a programmer, Spark programmers are already very used to the idea of writing less code. In this example, I'm showing a relatively simple computation. I've got a list of names, and I've got a list of ages. And I want to find the average age for each name. So in MapReduce world, I won't spend too much time on this, but I have to start by writing a map function that actually does data parsing. And then I write a reduce function that actually does the computation. And of course, Spark made this significantly more concise. Just with RDDs, I can express that computation much more easily, removing a lot of the boilerplate. But still, looking at that, that's not a terribly easy thing to understand, right? There's a bunch of ones and zeros, and I'm not really sure what those relate to. I had to do my own parsing. So if the data format rearranged the columns, my computation is going to break. And so the nice thing here is DataFrames actually takes this a step further. So in contrast to the Spark example, the data comes in pre-parsed. The table understands the schema, and I don't have to worry about pulling the columns out of it. When I want to work with individual columns, I access them by name instead of by ordinal. And what that's going to be is it's going to give you a significantly more concise expression of your computation. So we've got full API docs. This same kind of API works in all the languages Spark supports. These links work as well if you download this presentation later to all the various libraries. But really, it's not just about less code. It's also about making your program run faster. A question I often get is, I'm a Python programmer. Am I paying a performance penalty for using Python instead of Scala? And with DataFrames, the answer is no. It's all using the same execution engine under the hood, and so the performance is exactly the same. This is that aggregation example code from the previous slide. We wrote a very simple Python implementation. We even wrote a naive Scala implementation. And the DataFrame version, and no matter which language you're using, SQL, R, Python, or Scala, has better performance and is uniform across all the languages because you're leveraging the exact same computation engine underneath. So now I want to do a quick demo where basically I'm going to take some of that data from that slide before. So I created this table with Jira data, and then I'm also going to load some data from GitHub. Now this actually isn't an artificial example. I recently returned from my honeymoon, and when I came home, there were 100 Jiras 100 PRs waiting for me to review. I had no idea which ones to review first, and so I wanted to come up with a system that would make this easier. The demo that I'm going to be doing is going to be running inside of Databricks, which is a hosted version of Spark. You may have seen it this morning. But let me just say that we're strong believers in open source, so everything that I'm doing in this demo, you can obviously also do in the Apache Spark distribution. So let's go ahead and pull this up. The internet is working. It's a good sign. OK, so here I am in Databricks Cloud. And I'm going to start by querying this Hive table that we looked at earlier in the presentation. Select star. So select star from Spark SQL Jira. And so this is loading that Parquet data, inferring the schema from the JSON. And you can see here is all of the data that the Jira gives me. One of the nice things about our JSON and our Parquet and our other kind of complex data format support is that we actually maintain any nesting that exists in the data. So you can see I've got some nested objects. I've got arrays as well. And all of those are preserved. That structure is still there, and I can query it just like I would query it if I hadn't loaded it into a SQL database. So this is not your grandfather's first normal form database. So now that I've got this data set, I want to actually combine it with data from another place. So we've got this really nice website that a lot of the Spark developers use called the Spark PRs dashboard. This was written by Josh Rosen. And you can see it kind of gives me a view of all of the PRs that are currently open, all the code people are trying to add into the Spark project. And one nice thing is it actually exposes its data over a REST API. So I just loaded this REST API here, and I've got a bunch of JSON data. So I'm going to copy that URL, and I'm going to go back over here, and we're going to load it in. So raw PRs. So we'll start off with SQL context read. So we'll start that builder pattern. The format will be this custom data source that I created, Databricks, Spark, REST. So I wrote a REST data source that will read any JSON REST API over HTTP. And it needs to know the URL in order to download the data. And then we'll say load to actually make the computation occur. Oh. And so, zoom in, sure. Everybody can read that? So what I've done now is I've created this new data frame, reading this data over REST, and now I've got this data frame back. So if we take a look at it, you can see once again now it's extracted all this data, all the nested structure is still there. And so now I can do slicing and dicing on it. So I've pre-done this part, but basically I can do things like take an array and explode it out so that each element of the array, instead of being kind of a flat array, is now going to give me one row per element. I can use UDFs to do concatenation and other manipulation of the data, and I can select out the columns that I actually care about. So, and then I'm also going to do a filter here to only pull out the SQL queries. So now I've kind of sliced and diced and structured this data the way I want, so I can actually join it with another data source. So now I'm going to pull up this table again, table Spark SQL Jira. I'm going to join it with Spark PRs. And I'm going to specify the key that I want to join on. So I'll join the Jira key with the PR Jira. And what that's going to give us is another data frame with all of the results together. But of course, we're in a web browser, so we can make this look quite a bit nicer. Let's actually visualize this. So it's actually executing this query and bringing the results back. And what we've got now is all of the data from both of these data sources together. So I can see things like the Jira and the priority and the issue type, but I can also see the PR and whether or not it's passing tests and who has been commenting on the PR on GitHub, all in one place. So really what this does is it makes it very easy for you to take data from a variety of sources and get it together so you can do the analysis that you want to do. So I'm going to jump back to my slides now. So that was a demo in Databricks Cloud. If you want to try that out, you can sign up at accounts.cloud.databricks.com. But like I said, all of this code will be available online. Just follow my Twitter feed. So how did that all work? What actually happened under the covers to make that happen? So a big part of it is the Catalyst optimizer. And a key thing here is that DataFrames and SQL share exactly the same execution pipeline. Basically, all either of these is doing is constructing a logical plan, which we then optimize and execute using the same optimized engine. And so what this means is that it's seamlessly integrated with the rest of Spark. So when I want to use UDFs, unlike other systems where you would have to compile a jar and upload it and register it with the system, all you need to do is pass a Lambda function to the UDF function, and you immediately get back something that is a UDF that I can use inside of a data frame operation. So in this example, I'm kind of showing how, this is once again in Python, but this works in any of the languages. I'm showing how you can both declare UDFs and also use the programming language to make your data frame operations more composable. So consider you're some sort of ad tech company, and a very common operation is for me to get streams of events from different sources, and I always want to add demographic information so that I can do machine learning. In this example, one of my coworkers has written for me this function, add demographics, that takes any data frame that has user ID and adds all of the possible demographic information that we could need to it. So it loads this Hive table user, it does a join, and then it also does UDFs to kind of do more complex processing, for example, turning a zip code into a city. So once I have that, I can actually I can use this function elsewhere. So I take that function and I actually pass in some JSON data that I have. So I'm doing a SQL context load, and then I'm calling the add demographics function, and I'm getting a new events data frame that has all of the data I need to do my machine learning. But now I want to hone in on one specific population. So I'll look for only the people who live in San Francisco, and I only care about one column. I'm doing some temporal analysis where all I care about is the timestamp. So what you should see here is that in a traditional system, if we were evaluating this eagerly, if we weren't constructing logical plans for the data frame, we'd be missing a lot of opportunities for optimization. My coworker who wrote the add demographics function didn't give me any abilities to say which columns I cared about or if I was going to be doing any filtering. And as a result, this join would be very expensive. I'm joining with a whole bunch of users that I obviously don't care about because they don't live in San Francisco. But because we are executing it lazily, because we're constructing this logical plan, we can actually, at runtime, figure out that we can push this filter beneath the join, only join on the relevant users, and significantly speed up the operation. Even more, so this is kind of a simple example where I'm using JSON, but if it becomes time to productionize this, and I switch to Parquet and I partition my Hive table, Spark SQL is automatically going to figure out that the data formats have changed, and without you having to write any code, will automatically re-optimize the query plan and give you this more optimized version where it's pushed the filters down and actually done things like using Parquet, which is a columnar storage format, to only read the columns you care about. Or if your Hive table has predicates, it will also use those predicates to make sure that we only read the partitions that you care about. And so all together, sorry. So altogether, what this means is that, OK, well, I'll just keep talking. There's only 2 slides left anyway. OK, so yeah, OK, good. So that slide was too complicated of a machine learning pipeline for these projectors, I guess. But it turns out you can build very complicated machine learning pipelines. And because the DataFrame API is so expressive, what we've done is we've kind of actually built the entire machine learning pipeline API on DataFrames. And so if you want to check it out, you can go to Joseph's talk at 3 p.m., which is going to today at 3 p.m., which is going to talk more about the pipeline API. Another thing I'm really excited about is Project Tungsten. So we've been talking a lot about this, but really DataFrames are at the core here, because again, we've got a lot more schema information. So we can do significant optimizations that would not be possible with traditional RDDs. So these are just some very initial results, but basically what Tungsten is going to allow us to do, it's going to allow us to take that schema information and tightly pack data into the memory, avoiding GC, avoiding serialization costs, and basically allowing the system to be significantly faster and more robust. So that's my talk. I think I've got a little bit of time for questions. And there's also a bunch of office hours for the Spark SQL team. So come by the Databricks booth and check it out. Thank you very much.
Hi, Michael. If you like, we have time for questions. There are mic stands on the aisles, so we can take 2 questions. All right.
How about right there?
Hi. Is there any way in which you can invoke machine learning Spark ML functions from inside of Spark SQL in order to, rather than retrieve the data through SQL and pass it into an algorithm, could I invoke the algorithms through the functions like I would a SQL function?
So you can write UDFs, which would allow you to invoke arbitrary functions inside of SQL. But really, this is exactly what pipelines is about. When you specify the input and output to pipelines, you're specifying the column names of data frames, and it is wiring up the logical plan underneath the covers to extract just the data that you want. So I'm not sure that answered your question.
OK. Maybe I need to talk to you more offline about it.
Sounds good. Any more over here?
Hey, you guys demoed these custom aggregation functions that look really cool. Do you support the ability to write custom aggregation functions the way we can write custom UDFs?
Yeah, so you can write UDFs today, but you have to write them using Hive's API. So we kind of get this for free since we support all of the various types of Hive functions. However, in Spark 1.5, we're hoping to add a much nicer, simple API similar to our UDFs for UDAFs as well. So hopefully Spark 1.5, definitely by Spark 1.6. One more?
So first of all, thank you very much for the data frames. I've been using those. It's excellent. One question that I have is the performance vis-a-vis Hive. So I found, for example, that if I just go into Hive and do a query, and then do into my SQL context, and then do the same query or Hive context, there is a big performance difference. Can you comment on that?
You've seen a performance difference between the SQL context and the Hive context?
No. So if I just go Hive by itself, so not within Spark. So if I go like Hive and do the same query, and then go it within Spark and do a Hive context, and exactly the same query, there is a big performance difference.
Is Spark SQL faster?
I wish.
Okay, well, if there are any queries where we're slower, I would love to figure out why, but I'd have to see the specific query.
Yes,
in general, I've seen it to be significantly faster. So let's figure out what's wrong there. Is that it? Okay, I'll be around for other questions afterwards. Thank you very much.